All right. So 6.1 is talking about what's called the area between curves. So we've done some work with area, right? But it's always been the area under the curve. So I've given you some function like this and said, you know, what's the area between A and B? Right, and we know the area between A and B is just the integral from A to B. What we're hoping to do in chapter 6 is to kind of expand your idea of what the integral really is, this definite integral. So right now, this is kind of all we think of with the definite integral, right? It gives me the area under the curve. And again, that could be positive or negative, right? And there's some other things involved in that, but it's fundamentally just like the area under the curve. But that area has some actual applications, and its result has sort of, how do I want to say this, some other meaning to it when we're dealing with other situations. So what I'm hoping we get to at the end of chapter 6 is that we see this expression here as not just area under the curve, but this is a tool for adding, let's say, stuff together. Okay. So the way it's set up, or the way we think of it now, the stuff that we're adding together, I should probably put quotes around stuff, right? None of this is very mathematical at this point. But the stuff we're adding together, remember where this expression comes from, right? This is the limit, this whole thing, right? The limit as n goes to infinity of the sum from I equals 1 to n. F of x of I times delta x. That's what this is. So this f of x dx is really corresponding to this piece here, right? And this piece here, if you remember where this came from, this was the height and this was the width of these little rectangles. So we looked at that curve as a series of rectangles, right? And we added them all together. Then we let the number of them go to infinity, and that's what the value of that definite integral is. And so that's why we have area here, is because what we're adding up is little rectangles. But if we change what we're adding up, so this expression is now representing something different, this tool will still add all these things up and let the number of them go to infinity. So these I don't know, little pieces can be little pieces of anything. They can be little rectangles like we have here, but it could also be little pieces of work, like in physics, little pieces of work, or little distances, any sort of things that we want to approximate and then find an exact value of, we can use this tool to accomplish. And that's where this definite integral sort of loses its restrictions and becomes a tool for us to really calculate all kinds of things that were not possible before in this infinitesimal way, right? The limit as n goes to infinity is the new calculus idea. And to be able to apply that to adding up different things is a powerful kind of tool. So in 6.1, we're still working with areas, but now we're thinking of, we want to know the area between two curves. Okay, so we have some function f and some function g, and I want to find the area between them, right? Which is this region in here. Now, geometrically, we could probably figure out how to do this by sort of looking at two different areas. But what I want to do is I want to set up an integral that when I solve it is going to give me what I'm interested in, which is the area between these two curves. And so what I want to do is I want to try and approximate the area under these curves. And it should feel quite familiar to think of approximating it, right, using this rectangle. The width of this rectangle we would call delta x. And the height of this rectangle, it's not just f of x sub I, because I only want this portion, right? F of x sub I is the whole value from the x-axis up. So I would need to subtract off g of x sub I. And as a general rule, when I want a distance here, the distance is the larger minus the smaller value. And that's going to be useful in chapter 6.1 and 6.2 and 6.3 as well. So we're trying to lay the groundwork here for our later sections as well. The distance is equal to the larger value minus the smaller. Okay. So this distance from there to there. The larger value here is f of x sub I, and the smaller value here is g of x sub I. So if I subtract those two, I get the distance that I want. So the area of this little rectangle is going to be that height, f of x sub I minus g of x sub I. That's the height times the width. And then to get the area under this curve, I want to add up all of those values, right? This is an approximation. What we're missing, of course, is the limit. So this is really just like, at this point, just an expression for the area between those two curves. What we can recognize, though, is that this is really like exactly the same basically as this, right? The function is different, but everything else is the same. So this is actually a definite integral as well, right? And we know lots about definite integrals. We feel very good, hopefully, about definite integrals. So this becomes the definite integral from a to b of f of x minus g of x dx. And, you know, depending on what f and g are, this is certainly a definite integral that I could find the antiderivative of and then use a fundamental theorem to calculate it. And so there is a subtle change in what we're doing, right? When I see this expression, I'm really thinking about this expression, right? I'm really thinking about, okay, what am I adding up? I'm adding up some heights times some widths, and that's going to give me these areas, right? And when I add them all up, that's accomplished with this definite integral. Okay. So let's see an example of this. try the area between f of x equals x squared and so g sorry g of x. Let's try x plus 6. Okay. So very clearly, this is an area between curves kind of problem. When we're dealing with these problems, we do need some kind of graph of the situation. We don't need a precise graph, but I need a rough idea because I really need to see kind of how the functions are interacting so that I'm sure that I'm adding up the right things. I can't just blindly take f of x minus g of x and plug it into a definite interval because that may or may not be giving me exactly what I want. Most of the functions you will see are going to be functions you know, so that's nice. But if you didn't know them, you know, technology would be a good way of coming up with a graph, or just plotting some points would also work. So there's our x squared, and then g of x equals x plus 6. Right, I get something like that, and I can see that the bounded area, which is the only area I could calculate, would be this inner region here. So, just like before, it's nice to draw what we think of as a representative slice. Like one of those little sections that I'm going to add up. And that representative slice can sometimes help me kind of set the problem up properly. The other thing I need to figure out is I need to set where I am integrating this from, because remember, our goal here is to come up with a definite integral, which means I need an a and a b. So I don't want to like add this together randomly. I want to add exactly over the shape that I have, right, which would be from there to there. So I need to calculate what those x values are so I know what my bounds might be. So those are kind of two separate things that I need to do. I can do them in either order. Let's go ahead and find the bounds first. If you want to find where two functions intersect, you just set the functions equal to each other. So we get x equals 3 and x equals minus 2, which notice it doesn't match up with my picture, right? It looks probably like it's a little further over here than it is here. And that's one of the advantages of the picture, right, is that you can sort of verify that your work makes some sense, right? And that was something we like to do in our labs too, right, is use the graph and use our work and make sure everything fits together. And then I need to add up the height of this function, right? And what I talked about before is we take the upper value minus the lower value. So this upper value is f of x, equals x plus 6. That's the top value, right? That's the y value up there, the height of it, minus the height down here, which is equal to x squared, right? The y value is equal to x squared all along this curve. The dx represents our width. It's a 6 there. Okay. Questions about this setup? The setup is really the critical part, to be honest. Once you set it up, then this integral just is what it is. You got to work through it and see what happens. If you set it up incorrectly, of course, you're going to get the wrong answer. So you gotta, that's where you want to put in your effort, is really getting the setup correct. And I'm not afraid of asking questions even on the final that just say set up the problem, and in which case your answer would be right here. In this case, this one is not too hard to continue. We would find the antiderivative. And we would evaluate it from -2 to 3. So I put in 3, 9/2 plus 18. It's 27 divided by 3 is 9. I put in -2, I get 4/2 minus 12 plus 8/3. If I add all of that together, I'll get my answer, right? So we can do that. 9/2 minus 4/2 is 5/2. That's 9 plus 12. That's going to be 21. And then I have minus 8/3. Well, I don't know, it's going to be a little bit. It's going to be like some kind of sixth, right? 15/6 plus 126/6 minus 16/6. (125/6). Now, you know, that value, I can't look at the graph and tell you if that value makes any sense or not. It's hard for me to estimate areas. So I don't know what 125/6, that's likely or not. But that is the answer we're looking for in this case. Okay. So, you know, hopefully that part so far seems relatively straightforward. You can run into some situations where, you know, you have a function that does this and another function that does that. And so here we have to be a little careful, because if I integrate, so like over this region, f is bigger than g, right? So this portion here would be f minus g. But if I continued that all the way through here, all of a sudden f minus g, that would give me a negative value here. And then I'd be adding a bunch of negative areas to my positive areas, and I'd end up with maybe nothing, or certainly not the right answer. So what I would have to do in this case is I'd have to split this and integrate this region here over f minus g, and then the second region here would be g minus f. Okay, so I'd have an integral of f minus g, and then I'd add to that the integral of g minus f. Okay, so it makes it like a little harder to do, because you're really doing two integrals instead of one integral, but the structure of the problem is very similar. And you would just have to see that by your graph. If you run into some problems that are sort of hard for you to graph, feel free to use some technology to graph them to get a look at what's going on. I won't give you ones that are hard to graph. Or if I did, I would give you a graph of them. So you can, not have that part of it giving you trouble. All right. So there's one other complication I would like to show you. So what if we had two curves that looked like this? Now, clearly this first curve here is not technically a function of x, but it's still a curve. And I can write a formula for it. It would look something like x equals y squared minus 2, let's say. All right. So that would be this parabolic curve that's on its side. So not a function of x in our normal sense, but certainly a relationship, and there is an area there. And let's say this other line here, let's make that y equals x minus 8. Clearly my scale's off there. How about instead we do y equals x minus 1? Does that work? No. Sorry, I just want to make the numbers work out nicely for us here, and right now they're not going to. Well, let's make that 1 and this 1. Sorry, messy. All I'm doing is I'm just making it so that the bounds are going to be hopefully whole numbers here. Otherwise, it's much harder to actually calculate. It's fine. We would have to use the quadratic formula to solve it, but we don't want to add that complication here. So these two formulas represent my two functions. Okay. And I want to find the area between those two functions. Okay. The problem here is that if I try and do this area by adding up all of these rectangles, I run into some fairly significant problems. First of all, like over this first region, the top function is here and the bottom function is here. And so like I'm sort of using the same function as the top and the bottom, which seems a little awkward. And also notice the bottom function here sort of switches, right? Over this first region, the bottom function is part of this parabolic curve, and then as soon as I hit this x value over the second region, the bottom is this linear function. So I'd have to break this up into two separate integrals because those top and bottom functions switch. It turns out that's not a very good way of going about this particular problem. what I want you to notice is that what if instead I looked at adding up these rectangles? I sort of tilted the whole thing on its side. Can you see that I have none of the same problems here? I have a very consistent upper or larger value, right, farther to the right, and I have a very consistent smaller value here on the bottom. So the height here would be very easy to set up and find algebraically. I don't have to switch gears like I would have in this other situation. So this is the other kind of orientation that we can do with integration. And this is important in some of the problems in area, but it's also going to be very important when we get to our volume questions in 6.2 and 6.3 to be able to switch how we look at these curves. So if I'm looking at this kind of representative slice right here, it has a thickness. It's not going to be dx, right? Dx is like these problems here, right? Like this thickness. That would be a dx because it's like a little piece of the x-axis. This is a little piece of the y-axis, so that thickness is going to be dy. And that dy piece is important. That actually tells me, this tells me that all variables should be in terms of y. Y is my new variable here because of that expression being dy. Now I still need to figure out the sort of height, which in this case is sideways of this slice. The larger value is that x value, right? And the smaller value turns out to be like this little x value here. If you take larger minus smaller, you're always going to get the distance between them, right? That works because the smaller value here is negative. So when I subtract the negative, it's actually like adding it together to get that whole length. But these x values need to be written in terms of y. Okay. So for this back part here in the curve, well, that's actually quite easy. X is y squared minus 1. So this piece here is y squared minus 1. This piece is also quite easy. X, I gotta just add that over. X equals y plus 1. So I'm gonna take the larger value, which is y plus 1. I'm going to subtract the smaller value, which is y squared minus 1. That difference is giving me the distance of that little rectangle times the width of that little rectangle. This is going to add them all up as soon as I give it the right bounds and give me a value, right? And I'm going to do that using the fundamental theorem. So the last piece is I just need to figure out where these are equal. So like before, I'm gonna solve that for x. So then I can set these equal to each other. Y plus 1 equals y squared minus 1. And y equals 2 and y equals minus 1. That's why I had to do that thinking in the beginning. I was trying to make sure I would get a quadratic that factored. And I want the y values. So when I'm integrating, I'm adding up all of these slices over these y values. So from -1 to 2, everything is in terms of y when I slice horizontally. It's almost always easiest to combine these. +1, +1, +2. And we can do this, but let's not, right? It's just a polynomial. You can find its antiderivative and calculate that value. It's the same problem, but we are less familiar working with y's than we are with x's. It's important that we are able to, both for the problems here, but also for the problems in 6.2 and 6.3. So if you can understand this concept here, it's going to help you a lot, because we're going to need to be able to switch between x's and y's when we look at 6.2 and 6.3. So some clues onto when I should switch. The biggest clue actually for this problem was this. This function is written in a way that it's easy to change x's into y's, but it's a little tricky to change y's into x's, right? I'd have to solve this and the square root, and I get a plus and a minus, which should actually be like the top half and the bottom half of this. So it's not very easy to change this in a way to make it dx. Dx would mean I'd have to change the y values into x's. That's hard to do the way this equation is written. Much easier to change the x's into y's, which means it's easier to have these slices horizontal, right? These dy slices rather than dx slices. Questions about that? These, I think sometimes feel like tricky problems. There's nothing inherently that hard about any of the steps. I'll just say it's not some very obscure or hard steps here, but it is a newer way of looking at the problems, and so that can make it challenging, right? And you have to understand where all the different little parts are coming from, and that's also not trivial, right? To figure out where and how I put all these pieces together. So I would, again, encourage you, as always, to keep looking at the videos that I have up as well, and work through these examples. Draw some pictures to help organize your thoughts, and be very conscious about when I'm putting in x's and when I'm putting in y's and how those are fitting together. Okay. After going through it and talking through that, I feel actually like that's pretty good for right now, for giving you some things to think about and work on.